that you were talking about molarity, was looking at the number of moles in a liter of solution. When you're looking at percent solution, that's out of 100. Well, what if you have really, really small amounts of solute? So instead of having like 5 grams per 100 mils, which is a percentage, like percent solution, what if you have 0.000005 grams of something? Toxins can sometimes still have an effect, even though they're found in a really low concentration. So that's where parts per million and parts per billion come into play. Okay, so parts per million, by definition, is just how many parts you have compared to a million parts as the whole versus 100 or even a liter. So we're talking about a large volume and a very small solute amount. The easiest way to solve any of these is to put the units, put your mass of your solute in grams, then divided by the volume of the solution, but make sure the unit is in milliliters. Okay, so whatever your mass amount is of the solute, put it in grams, put your volume of your solution in milliliters, and then if you want to convert to parts per million, you multiply your answer times a million. If you want parts per billion, you just multiply that answer, whatever you get in this math, multiply it times a billion. So here are some examples. So in this first one, if I want to know parts per million, and I didn't even tell you what the solute is, but I know that I have 12 milligrams of solute, right? So this is my solute. And I know that it's in 250 milliliters. That's my solution. So the mass amount of my solute, I want to put it in grams. So this, I'm going to have to convert to grams. 250 milliliters is the unit that I want for my solution. So I'm going to use that as is. So that one's good. Okay? So in each case, look at the solute amount. If the solute is anything but grams, you're going to have to do a unit conversion. So 12 milligrams is equal to how many grams? Well, that's just a single step, right? So remember what you do. You put down what you're given, times in the line. What unit goes on the bottom? Milligrams goes on the bottom. Grams goes on top because that's what I want. Milli gets what? 1,000. Milli is always 1,000 in front. The grams gets the 1. So you take 12 divided by 1,000. Gives you 0.012 grams. So that is the mass of my solute in grams. So now I need to divide it by the volume of my solution in milliliters. And in this one, I don't have to convert milliliters because it's already in milliliters. So I'm just going to put that 250 milliliters, the volume of my solution. Whatever this answer is, I'm going to multiply it times a million because I want to know parts per million. So remember, a million is a 1 with 6 zeros after it. 0.012 divided by 250. Whatever this answer is, I just say times 1, 2, 3, 4, 5, 6 zeros. Okay, so do the math. 0.012. Divide it by 250, then multiply it times a million. I got 48. So this would be 48 parts per million. Did you get that?
I did, but I may have did something wrong.
So 0.012 divided by 250 times a million. Should have gotten 48. Right? Because this times. So 48 parts per million. That's a way of describing the amount of that solute, that very small amount in such a large volume. So they give you the reference. They say you can think about a parts per million is like 5 drops of food coloring in a bathtub of water. So that's a really small amount. So percent wouldn't work with this because percentage would be so much, it'd be like 0.0000048%. So it'd be a really small percentage. So using parts per million puts our solute amount in a more measurable number. Let's try the one underneath. So the one underneath is in parts per billion. So if I have 0.89 milligrams of my solute and it's in 12.5 liters volume of solution, how many parts per billion would that be? So if this is my solute, I know that I have to convert that to how many grams it is, because it starts in milligrams, so I'm gonna have to do a unit conversion. 12.5 liters, I need it in milliliters. So this is the solution, and I need to convert that one to milliliters. So this one, I'm gonna have to convert both of those. 0.89 milligrams times in a line. I've got to go to grams, so milligrams on the bottom, grams on the top. Milli gets the 1,000. We do this, 0.89 divided by 1,000. Would be 0.00089 grams.
0.89.
Divided by 1,000, right? So 0.00089 grams. Now I've got to convert the volume. Did you get that? Put in your calculators, 0.89 divided by 1,000.
Keep coming up like this. I think that's me.
Is it telling you 8.9 times 10 to the minus 4th?
Oh, that made
It's just putting it in scientific notation for you. Do you know how to switch it back to the regular standard?
Tell me.
I don't know. I'd have to look at it.
Yeah, I
Like,
think so.
those graphing calculators. All right. I've also got to do this though. The 12.5 liters. I'm going to put it up here so you can see it a little better. 12.5 liters. I need to convert that to milliliters. So I'm going to take 12.5 L times the line. What unit goes on the bottom? Liters on the bottom, milliliters on top. And again, it's just a single unit conversion. Milli gets what? The 1,000. Liters gets the 1, right? Milli always gets 1,000 in front of it. Yeah, I just don't have room down here, so I just put it up high. It's this. I'm solving for the converting 12.5 liters to milliliters. So that is 12,500 milliliters. Okay? So that number is what my volume of the solution, 12,500 milliliters. And whatever I get from that, I have to multiply that times 1 billion. And 1 billion is a 1 with 9 zeros after it. So I'm taking 0.000.12389 divided by 12,500 equals then times 1, 2, 3, 4, 5, 6, 7, 8, 9. Like I actually have to make myself count those zeros as I put them in. Oh, it's not, it should, you're right, you caught it. It should just be 12,500. Yeah, because that 12.5 becomes 12,500 milliliters, so 12,500 milliliters goes on the bottom. So it's still ml.
So you went back down now.
Yeah, I just took this number, and it's the number I put right there. Just because I didn't have enough room. There's really not enough room to do 2 unit conversions down at the bottom. I'd have to write teeny tiny small. So that 12.5 liters is from this parts per billion problem. I just have to convert liters to milliliters. So in this one, I had to do 2 unit conversions. But once I get done, see that you put, just make yourself a note. Put your solute mass in grams. Put your solution volume in milliliters. Okay? Then grams divided by milliliters times 1 million or times 1 billion is how you solve for parts per million and parts per billion. So this number I got was 71.2. I got 71.2, and that would be ppb, parts per billion. Did anybody not get that? 0.00089 divided by 12,500 and then multiply it times a billion,
I'm in
which is
9.
9. Just make sure that you hit. Like I literally count the number of zeros because that's one of the errors that I constantly make. Now, if you were going to round these, the first one I wouldn't have to round because the first one's 48, 2 significant figures. 12 is 2 significant figures. 250 has 2 significant figures, right? So that one has 2. This one has 2. So I'd be fine with 48 because that's 2 significant figures. But if I was going to round the second one, 0.89 is how many significant figures? 2. So I'd have to end up rounding, since that one has 2, I would only keep the 7 and the 1. I'd drop the 2, so it would end up being just 71 parts per billion as a number. That's if I had to give you that. But normally you don't just calculate parts per billion to calculate parts per billion or parts per million. Instead, you calculate parts per billion and then you compare it to a standard, because parts per million and parts per billion is really a way of calculating safe or toxic levels of very, very small amounts of solute. So for example, copper in drinking water is toxic if it's above 1.3 parts per million. So your drinking water that goes through the water treatment plant, it is actually tested routinely for many very minute solutes, very small amounts of solutes, to check and make sure that people are not being poisoned because of their drinking water. And if you've ever read any of the news about places like Flint, Michigan, oh God, their water, they have been drinking bottled water for years.
Yeah, more than 6 now.
Years. Their water is not safe to drink because of all of the heavy metals that they use in the car industry. So like chrome plating, using solder, all those heavy metals have seeped into their water, and it's not safe to drink. So they literally, people bring home cases and cases and cases of water. You're really not even supposed to brush your teeth with it. You are not supposed to cook your food with this water.
Bathe in it.
It's terrible. It's terrible. So the copper in drinking water, if you're given an amount,
they're gonna die, aren't they?
I don't know how long that exposure, but they have shown that their disease rates are higher on average than the nation.
Yeah.
Because of that.
Well, why would they allow people to stay in that area?
There's it's the same. There were people after Chernobyl that still live in that area. They just refuse to leave. And for some people, they can't afford to go anywhere else. Where are they? If their job is there, they're kind of stuck there. Where else would they work? Where else? How would they move? Where would they move to? There's a lot of that comes into play as well. So this is the most common reason that you end up with a parts per million or parts per billion type of question, is it's relative to what the normal would be. And so you're trying to figure out, is this a normal safe level or is it above what it should be? So for example, if you test 500 milliliters of water sample and you measure 150 micrograms of copper, is this safe to drink? So remember what you have to do. One, you want to know parts per million. So I know that I need to put my solute in grams. I know that I need to put the solution in milliliters. And then I'm just going to multiply my answer times 1,000,000. Okay, so in each case, my solute amount is not in grams, it's in micrograms. So I have 150 micrograms, and I need to convert that to grams. It's still,
Put it in million.
and I'm gonna have to multiply it times 1,000,000 at the end.
You don't have enough zeros.
1, 2, 3, 4, 5, 6. Did it go off of the page?
Should have.
I have. There's 6. I tried to write them really small. Okay, so the first one I want to do is I want to convert micrograms to grams. 150 micrograms times in a line. What unit goes on the bottom? Micrograms. Whatever you're given always goes on the bottom. What I want to go to is grams. Micro, what goes in front of that? Do you remember? Milli is 1,000, centi is 100, deci is 10, micro is 1,000,000. Right? So anytime you have micro, 1,000,000 goes in front of it. So if I take 150 and divide it by 1,000,000, decimal place moves to the left 6 places. So I'd have 0.00015 grams. So that's the number, the amount of solute in grams. Now I need my solution to be in milliliters. This is what I've been doing all day long. Putting my sweatshirt on, taking it off, putting it on, taking it off. Now I'm hot. Okay, so I want to put my solution volume in milliliters, but it is. So I have 500 milliliters. I don't have to convert that. That's the volume that I want. So 0.00015 grams divided by 500 milliliters. Multiply this times 1,000,000. What'd you get? No. I got 0.3. Try it again. When you get this answer, you compare it to the limit that is listed. So it says drinking water is toxic above 1.3. So if our level is 0.3, then it's considered safe. Did you get 0.3?
If it's 0.3.
Right, so look at, when you read the question, copper in drinking water is toxic above 1.3 parts per million. So ours is 0.3, so it's lower than 1.3, so it would be considered safe. So you could have copper in your water because of old pipes. So the copper, over time, it begins to erode, so you can end up with copper in your drinking water. So you try this one. Same thing, whether it's parts per million or parts per billion, you got to put your solute in grams, put your solution in milliliters. But this one, since it's parts per billion, multiply it times 1,000,000,000. 9 zeros.
What is that symbol right there, the one that's up top?
Yeah, micro, the little u, that's really a mu. Remember, that's that Greek symbol for the micro.
not safe.
Why?
It's too much.
A lot?
I don't think so. I mean, from what I got.
All right. Did you get it? Wait for the math. Okay, she's almost there. So in this one, you've got to do 2 unit conversions, right? So you've got to go from milligrams to grams. Then you got to go from liters to milliliters. So before you can do the math, you've got to first put those in the right units. Good. Okay, so the first one, I took 0.08 milligrams and converted it to grams. That ends up being 0.00008 grams. Then I had to take 7.5 liters and convert it to milliliters. So that ends up being 7,500 milliliters. So then I've got to divide those. So 0.00008 grams divided by 7,500 milliliters, and then multiply that answer times 1 billion. And I got 10.66666667 parts per billion. So yes, it is above the limit. Arsenic is toxic above 10 parts per billion. So yes, this is toxic. Would not be a safe. They'd have to do remedy to try and bind and remove the arsenic from that water sample before that would be safe to be able to drink. Significant figures, if you were going to look at significant figures, always use the measured numbers. So I'd have to use 10.8, or sorry, the 0.08 and 7.5. So in this, 0.08 is one significant figure. So the problem with this is if I want to have only one significant figure, what would my answer be?
1.
Not 1,
10.
10. So then you would look at it and you go, oh, well, it's okay because it's 10. But in fact, it's 10.67 or 10.666667. So you would still say, compare the whole number to what the level would be, because it would still be above 10. Even though if I had to round this, I would round this to 10 parts per billion, according to significant figures, but according to the actual numbers, it's above what it should be. Does that make sense? Okay, because 0.08 is only one significant figure, and that would end up causing me to round it down and make it look like maybe it was okay, when that would not be okay. So if I asked you what is the parts per billion with proper significant figures, you would tell me it was 10. But if I asked you, is this safe to drink? You would compare that big number, the whole number off of your calculator, compare it to what the chart would say or what your level limit would say, because that would determine if it was safe or not. Because anything over 10 would be an issue. You can't just round down. That's like telling the police officer you rounded up on the speed limit. I know it said 65, but I just rounded up to 70.
You can't do that.
They won't be okay with that. They take it as an exact number. Okay, so everybody got those for that number. So there's an extra one. So the last math in this chapter, promise, the last math, and I did bring the practice ones, but what I want to do is get through this last math and then the theory stuff that I wanted to finish in chapter 8. And then I was hoping we had enough time to be able to do a couple of the practice problems that I have on that single half sheet. So the last math thing is about, well, what if you have a liquid, a mixture, and you want to decrease its concentration? So how do you do a dilution? How do you actually set that up? And so the one example, so for me, yeah, you have the little squirt bottle. Like, I don't know if you've ever used the little flavored squirts. So you can buy these little like flavorings that are in small bottles, and one squirt goes into a liter. You shake it up and it sort of has a fruit flavor of some sort. Some people say that they can't drink plain water. They have to have some kind of flavoring in their water. And so, I mean, it's kind of, if you can abide by the flavor of some of this stuff, because some of those I'm like, it's a little bit strong for me. But by adding that squirt of concentrated solution, adding it to water, you're diluting it, right? Well, you can actually calculate the exact amount of a concentration and volume of a solution by using a formula. So in this one, if I know 3 of the 4, I can solve for the one that I don't know. So C initial, I always call that C1, times the initial volume, the amount of the concentrated. So this is always your concentrated solution, because that's what I'm starting with. So this is the concentrated solution. If I take the initial concentration times the volume of that concentration I use, and I add water to it, I can dilute it, and I can make it equal to a final concentration at any volume that I care to make. So C2 and V2 are always the diluted solution, right? Because it's what you end up with. So if I take if I take C1, I take solution 1 and add water, I'm going to make solution 2. So solution 1 is always more concentrated. Solution 2 is always more diluted. Okay? And this kind of reminds me of Boyle's law in terms of the way that the formula looks. Like remember P1 times V1 equals P2 times V2. So this is really the same sort of way that you're going to set it up. You will always know 3 of the 4. You just have to rearrange your formula to figure out the one that you don't know. So it's here, this one. So you find a bottle of 22.5% magnesium oxide aqueous. So 22.5% MgO aqueous means it's a solution. How would you dilute it to make 650 milliliters of a 4.0% magnesium oxide solution? So what is 22.5? Is it C1 or C2? It's C1, right? It's the higher concentration. C1 is always going to be greater than C2 because it's always more concentrated. How would you dilute it to make 650 mils of 4.0% MgO, magnesium oxide? 650 milliliters would be what?
The volume?
Volume of 1 or 2?
2.
2. So 650 milliliters, that is V2. And the 4.0% magnesium oxide is?
C2.
C2.
You know I know this stuff when I'm in class. I go home with it.
So what don't I know? I don't know V1. So C1 times V1 equals C2 times V2. So I got to get V1 all by itself. What do I move? C1. So divide both sides by C1. That's going to cancel them. So V1 gets all by itself on one side of the equation. And then just plug your numbers in. So C2 is 4.0%. V2 is 650 milliliters. C1 is 22.5%. So it's 115.55555 milliliters. So if I have to round this, 22.5% is how many significant figures? 3. So this one's 3. 650 is 2, and then 4.0 is 2. So I need to keep my answer at 2 significant figures. So the first 2 ones I keep, the next number's a 5. So what will that do? So it'd round up to 120. So I would take 120 mils of that 22.5% solution. If you're doing a dilution, then you do know how much water you would add because they're all liquid volumes. So if I'm using 120 milliliters of that 22.5%, then how much water? So what's my final volume? So in the question, what's the final volume I make?
Should they go on the calculator in these parentheses?
You don't have to do them in parentheses. I put them in parentheses so you can see what they are. So if you just take 4 times 650 divided by 22.5. So what's the final volume of my solution I want to make? It's really V2. What is V2? So 650 mLs minus, what is V1? 120. So if I just subtract those two, 530, that tells you how much water you would need. So you can just subtract the concentrated volume from the final volume, and that'll tell you how much water you would end up using in order to make this solution. So remember, when you make up percent solutions and molarity, those you're taking a solid and you're adding water to make a total volume. So you really don't know the volume of water that you're adding. You just know you have to add enough. But with this, you actually do, because you're starting off with the liquid and you're adding water in it to make a dilute liquid, so you know exactly how much water you end up using. Okay, so here's another one. Try this one. What was the original concentration of a glucose solution if you use 275 mils of it to make a 1.7 liter for 5.25% solution? As long as units are the same, if both of your volume units are the same, both of your percent units are the same, like you can't use molar and percent, okay? You can't multiply if you have milliliters and liters. You're going to have to do a unit conversion on one. So always check your units and make sure that the units on both sides of the equation are the same. But see if you can set this one up. 33.
How much you put my numbers on? Everything.
All right, got them set up. All right, so the steps, and maybe I made a mistake, maybe not, I don't know. All right, so remember C1 times V1 equals C2 times V2. So then first question, what was the original concentration? So that tells me right away, oh, I need to know what C1 is. So that's my unknown. What was the original concentration? So I know that one's I don't know. If you use 275 mils of it, so I know that's V1, to make 1.75 liters of a 5.25% solution. So C2 is 5.25%, V2 is 1.75 liters, but before you can do the math, you have to look and see that the two volumes that I know do not have the same units. So one is 275 milliliters, the other one is 1.75 liters. So I have to convert one of them. It doesn't matter which, because the units will still work out. If you converted V1, you're fine. You should still get the same numbers. If you converted V2, I just converted V2 because it was on the bottom, and so I said, okay, well, 1.75 liters is how many milliliters? And I had to convert, so ends up multiplying times 1,000, so it was 1,750 mils. So now that I've got that, I have to rearrange the formula because I want to find C1. So I have to divide both sides by V1. So see that that moves V1 to the other side. Then just plug in the numbers. So C2 is 5.25%. V2 is 1,750 milliliters. Divided by V1, 275 milliliters. When I hit equals, I got 33.4090991.
I got 0.33409.
0 point. So
I didn't add the zero to the I didn't add the zero to the 175.
well, yeah, so 1.75 times 1,000 is going to move the decimal place 3 places, not 2. So see that 1.75 liters to milliliters, you multiply it times 1,000.
No, I just set it up like 5.25 and 1.75 divided by 275 when they gave me that.
Yeah, you can't, because one's liters and the other's milliliters, so they won't cancel. So notice the way that I have it set up, milliliters and milliliters will cancel. So if I have milliliters and liters, they're not going to cancel, and you'll be off by like a factor of 3. You'll be off by 3 decimal places. So do just make sure that you check. If you have volumes, if you have 2 volumes that you know, make sure you check the units. They have to be the same. And if one of them, if they're different, just convert one of them, and you can pick. It'll still be the same answer. If I had converted V1, it would still have turned out exactly the same. So then the last question, significant figures. So significant figures tells me that I've got 3 significant figures for 275, 3 significant figures for 1.75, 3 significant figures for 5.25, so 3. So that means I'm going to keep the 3, and the 4. The next is a 0, so what happens? Just drops off. So this would be 33.4%. See if there's, okay. All right, so that's it. That's the math, promise. No more math, okay? So there is enough math though. So if you have gas laws, that's at the very beginning of chapter 7. Okay, and then in here, we have all the solution chemistry. So that is doing molarity, percent solutions, parts per million, parts per billion, and then dilution. So those are sort of them. And I actually gave you kind of a practice sheet. And the practice sheet kind of like tells you, okay, remember, these are like the major things. Concentration, remember concentration times volume is the amount of your solid. What molarity means, what percent solutions mean. And we really do percent solutions in the M to V, mass to volume, where it's grams per 100 mils. Parts per million, parts per billion, and then that dilution one at the very bottom. So finish this up, and then we can go on and hopefully do a couple of those in terms of practice. But what I've got to do is I wanted to show you this demonstration. And so the demonstration, which is way, 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 way back here. The demonstration was talking about this, right? Do you remember this from the last class? Okay, so when we were talking about strong electrolytes, weak electrolytes, non-electrolytes, and after we did this, we did like this practice page of like how to split these up. So I wanted to show you, so I actually have a light bulb apparatus, and so the light bulb apparatus shows you, it's not OSHA. It's extremely old. Okay, but I have a light bulb and I have these two little poles that stick off, that hang off. So those are like those are like the poles, like kind of like this. So I'm going to plug this in. I've never electrocuted myself. Okay, so I brought a bunch of different solutions. Some solutions are strong electrolytes, some solutions are weak, some are not. First one though is just distilled water. So if I take and put the distilled water to these two little poles, there is not enough ions that pass from one to the other to carry an electric current. And this is also a good way to kind of rinse it just to get it started. But if I take, not that way, if I take salt, okay, so this is like a grade sodium chloride, so it's just salt. So salt is a strong electrolyte. So I know that salt is a strong electrolyte, but I need to do, I just labeled some of them so that I can remember for tomorrow. So I'm gonna have to put too much. So you see that I put some salt in there, and then now I'm just gonna stir it because I really want it to, for the most part, dissolve. I want it to do this reaction, just like the one with HCl and with Fe2O3. I want this salt to completely dissolve in the water and form lots of ions. Because if it forms lots of ions, then it can carry an electric current. It's a strong electrolyte. So pretty much? Okay. So now, if I put this on, okay. Huh? Distilled water cannot do that. The only reason that this does this is because those salt crystals dissolve, and now there's sodium ions and chloride ions that can float between those two electrodes to be able to close the circuit and light the light bulb. Okay? So, if I take and I'm just gonna rinsing the electrodes just with distilled water just to try and get any excess salt off. So that's a strong electrolyte. Good example of a weak electrolyte is this one. So this, give this a whiff. Does it smell like?
What smell like?
Can't smell it?
Oh, yeah.
What is it?
Let me smell it again then. It smells like vinegar.
Yes, that's exactly what it is. It's vinegar. Okay, so where's my vinegar? Here it is. Okay, so I want vinegar. So that's exactly what this is. Okay, so it's just vinegar in solution. They said it's about 4% acetic acid because it's not concentrated. But look, this is a weak electrolyte. So do you notice the difference? Sorry, Taya, I'm totally in your way. So do you notice, I'm moving back and forth. Do you notice the difference in the brightness of the light bulb? So this, it lights up just a little. That is because it's one of these. Weak electrolytes, remember we said that only a little bit of these form ions. So because it doesn't make a lot of ions, it doesn't carry very much of an electric current. So weak electrolytes are going to give you kind of like a dim light bulb. It's not going to be able to carry it. And that's why we have the arrows going in both directions. The arrow goes in both directions because most of the molecules remain solid or remains like as one. They don't form ions. Only a few split and form those ions. So that one's the vinegar one. So the bottom one, there's ethanol. So I brought some alcohol. This is just because I have to do this in lab. So I was like, let me try and keep these clean. Okay, so I did bring sugar or dextrose. Or no, I got ethanol. We'll do ethanol first. So here's ethanol. Okay, and then I got it in the ethanol bottle, so I'm just gonna dump the whole thing in here. No, the cat is falling to pieces. Jeez. Okay, and so even if I add a little bit of water to it, because you know ethanol is polar, so ethanol will mixes with water, like dissolves like and such. Okay, once it sort of settles, it'll be completely clear, so the ethanol does mix, but ethanol is called a non-electrolyte. So see when I put it up to the electrodes, notice that there's no light bulb that lights because there's no ions that are produced, even though it's totally clear, right? So it's totally clear, it doesn't form ions, and so it can't carry an electric current. So then I thought it would be interesting just to see, do you remember the saturated sodium chloride, right? So remember I was telling you, we talked about this in class. Do you see the salt in the bottom? Okay,
Shake it up.
so you were all in lab. I don't know that you weren't in lab. Did you make soap with us? Were you in the soap lab? Remember you had to measure this out, that saturated sodium chloride? So this is a bottle of saturated sodium chloride. Can you see the salt in the bottom? So this has as much salt as possible. So I was like, well, you know, this is probably going to be the brightest light bulb possible, because this is the maximum amount of ions that you could find present. So where is it? Here it is, saturated. So this is the
Which
saturated.
one is that of this?
So this is a very strong electrolyte
Okay.
because it's got as much ions as possible. So I was like, let's just see how bright it is compared to just the sodium chloride that I made where I just put a little bit. I was like, I hope this light bulb doesn't blow up.
Oh, you scared me.
Did you hear it pop?
Yeah.
It is very, very strong, okay? Compared to, the other one was just the regular sodium chloride, I only put a little bit in. And that was like, yeah, that one's bright. That one was like, kinda hurt that one. I don't know if I'm gonna do that tomorrow. So I'm just gonna rinse it one more time.
Could it blow?
I don't think so. I think it's kind of like a maximum amount of electricity that it conducts. So, but it's definitely, you can see a huge difference between the bright and the dim. All right, so then the other thing I brought is I brought sugar. Yeah, sugar, put some sugar in water. But you know that sugar is a covalent molecule, so sugar, table sugar, is not gonna light up the light bulb. It's a non-electrolyte because it's a covalent molecule, kind of like that ethanol was. I can show you just to dissolve this. And then I was trying to find another weak electrolyte, because vinegar's the best one, because vinegar always is like, works just right. Just trying to get this to dissolve. This is the sugar, that was pretty good.
Hold on, and the vinegar did light.
Yeah, but it was dim,
Yeah.
right? It was dim, so it's a good example of a weak electrolyte. So you see, this is the sugar water. So sugar water doesn't like the ethanol, doesn't really do anything because it doesn't form ions. So those non-electrolytes don't. So I found some boric acid. So I read somewhere that boric acid,
I need some of that.
boric acid was a weak electrolyte. And so I was like, well, let's try it. So I was literally in this chemical storeroom looking.
You know they took boric
Like
acid
trying
out
to
the
find
stores.
stuff, huh?
They took boric acid out the stores.
Why?
I don't know.
Are people using it to make meth?
Oh, I don't know about that, but I know it kills ants and spiders.
I know. Well, I gotta get it to dissolve. And the big challenge is trying to get it to dissolve. So if it doesn't dissolve very well, then it's not going to do such a great job. And it might have to be a good enough electrolyte to let, it might have some ions, but it might be so low that you almost can't see it. So I'm like, but it looks like it's dissolving. See? See any? Nope. So if it does, and some of it dissolved, if it does, I might leave it tonight to see if it does anything tomorrow. But it might dissolve real slow, and so we might have just not enough of this to be able to see it. So if only like 1% of the molecules form ions, And it might be such a low amount that you really can't see it. Just rinse my little electrode friend. I stole this from Wilson Community College. When I worked there from 95 until 2003. And then I came here and I was like, I'm taking this with me. Because I was like, this is the one thing that I think is really neat about being able to show you like what an actual electrolyte is. Okay? So then the other thing that I wanted to talk a little bit about, other than the concentrations, is I wanted to talk about transport, because this is at the end of dilution. Here. Transport of molecules is really the solute molecules. So dissolved in your blood, you've got sugar, you've got salts, you've got waste molecules, carbon dioxide. So the way that they get transported and move from point A to point B primarily is through osmosis or diffusion. So by definition, osmosis is movement of solvent molecules from high concentration to low concentration. So we are going to have movement of solvent molecules always from high concentration to low concentration. So the cell makes the cell membrane a semi-permeable barrier, right? So remember the phospholipid barrier of the cell, and it can control what things can move in and out. So water moves in or out of a cell if the solute concentrations are not the same. And it does this by using water channels that are in the cell membrane. If the solute concentrations are equal inside of the cell and outside of the cell, they call that isotonic. So the term iso means equal. The term tonic is really referring to solutes. So under isotonic conditions, the amount of water inside and outside of your cells stays the same. So we are constantly losing water. So you lose water from breathing, you lose water from sweating, you lose water in urination. So you're constantly losing water. So that is why you're constantly taking in water. So you're taking in water by drinking things, by eating things, and you try to keep this whole balance. If you manage to do that, if you manage to drink enough water during the course of the day, then you can manage to keep yourself in an isotonic condition. So isotonic means the fluid in the blood and the fluid inside of those blood cells is equal. If the fluid that is outside of the blood has less solutes than inside, so if a person drinks a lot of water, then it dilutes the blood. If you drink more than the balanced amount, then you're going to end up having a condition where the amount of solutes in the blood is lower than normal. They call that hypotonic. Hypo means low. Tonic means solutes. So a low solute fluid so you can think of a cell, and we'll think about it in terms of a red blood cell. So red blood cells, they look like little donut shapes. If there is less solute and more water outside of a cell, so that means inside of the cell, comparatively, there's more solutes and less water. The solutes are typically not allowed to pass, like sodium. Sodium, remember, is if there's a barrier for sodium to be able to pass through, phospholipids, the barrier of the cell membrane, won't let it pass. So the solutes can't move, but water can. Water can move through water channels to be able to balance it. So by definition of osmosis, water moves from where? From outside of the cell in or inside of the cell out. Water moves from high concentration to low concentration. So which way is water going to go? It's going to go into, water moves from where there's more to where there's less. So under hypotonic conditions, water will move into the cell and the cell will begin to swell. Now we did this with potatoes last week, right? So you put a potato in distilled water, right? So that was beaker number 3 was your potato that you stuck in water, no salt in the water at all. So that was our hypotonic condition. So that is where there was no salt outside of the potato. It was 100% water. So we had 0% salt, 100% water around that potato. And because we cut the potato, water could go in and out freely. So the water went from the distilled water in the beaker and moved into the potato. And what happened to the mass of the potato?
Got flexible.
No, other one. The third beaker, that potato got hard.
Yeah.
That potato, it weighed more.
Yeah.
So water moved in and it swelled up. So that happens to body cells. If a patient, this happens most commonly if the patient is dehydrated. No, not then. If a patient is dehydrated, so they come in and they've like, I've been vomiting, diarrhea, I'm sweating, running a fever. So you know that they're dehydrated. They have less water than they should have. And then they start trying to drink too much, too fast. That can actually cause this. That can cause the fluid outside of the cells to have too much water, and it can cause cells to swell. This is the whole old adage, like when you were starting to feel better after you've been sick and you're like, I'm thirsty. What did your mother always tell you to do? Just take sips, right? Did she always say, like, don't drink all of it at one time. Take sips, wait for a while, take some more, wait for a while, make sure it keeps it down. Make sure it stays down. I don't want to clean it up if I don't have to. But then also is to avoid this. Because if you're in a state of dehydration and you intake too much fluid at one time, that can cause that fluid of the blood to become hypotonic and cause water to then go into the blood cells and cause them to swell. Opposite, though, is what happens if, where's the other one? There it is. Is if there's not enough water outside of the cell. So again, you can think of a blood cell. If there is a high solute content outside of the cell, low solvent, which in our case is always water, inside of the cell, it's comparatively low solute and higher solvent. Osmosis says water goes from high concentration to low concentration. So water goes which way? So you see that it's high water in the cell would move towards low water outside of the cell. And this will cause the cell to do what? This was the potato that we put in the salt water. What happened to those potatoes? Yeah, they kind of shrunk down, right? They got really bendy, kind of like when you squeezed them, they're real kind of mushy feeling. So it can actually cause these cells to begin to swell and lose fluid. These cells, not swell, it causes it to shrink. So the cell shrinks. They call that crenation. This is what would happen if you drank seawater. So if you were drinking seawater, you would be ingesting very high salt. So the concentration of salt outside of your blood cells would go up. And that would actually cause the cells in your blood to lose water and shrink up. So just remember this analogy of the potato. This even happens though if you get dehydrated, because if you get dehydrated, you lose water outside of the cell because, like I said, vomiting, diarrhea, sweating, fever. So you lose fluid, you're not keeping fluid down. The amount of water outside of the cell goes down. Have you ever seen in a patient, have you ever seen tenting? Okay, it's really creepy. Like it's much more common in like children because they have a small body volume. So if somebody is severely dehydrated, their eyes will start to look sunken. Their skin almost looks like it gets saggy, like it loses all of its like little plumpness. And if you take the skin and pull it up like this, it'll like stay up. It won't drop back down. And that is because of loss of fluid from what they call interstitial fluid, which is the fluid up underneath the skin. That is because of dehydration. So extreme dehydration can put somebody in this hypertonic condition. But then when you try to hydrate them, you don't want to hydrate them too fast because it could cause them to flip and go the other direction. So here's a picture that actually shows like some electron microscope views of red blood cells. So you can really see what actually happens. So normal, what they call isotonic, physiological saline. Physiological saline is the concentration of sodium chloride in the blood, and it is 0.90% sodium chloride. So that's the normal salt solution in your blood. And if the salt solution in your blood is 0.90% NaCl, and it's the same inside of the cells, you have an isotonic condition. So notice that they show you that picture, the red blood cells sitting in the beaker. See the arrows look equal? So if any water goes in, it's equal to the water that goes out. And that's going to create the shape of what the red blood cell normally looks like. They call it a biconcave disc. The one in the middle is what happens if the blood gets too diluted. So if you go below 0.9% sodium chloride, there's not enough salt in the blood, too much water, water moves in, and see what happens to the red blood cell. See how it looks swollen, looks like a balloon instead of being kind of a flattened little disc? Worst case scenario, this can actually cause red blood cells to pop because they can't get but so big. They're not like balloons. Well, they're like balloons in my car, but they can't just go 10 times bigger. There is a maximum size that a red blood cell can expand to, and that can actually cause what they call hemolysis, which is breaking of blood cells. So that's if the blood is too diluted, so there's too much water. Can cause the cell to swell. So remember, hypotonic means low solute. Too much water, not enough salt. And then the last one shows you what happens if you get dehydrated, where you have not enough water. So the amount of solutes that are outside of the cell are greater than inside, and that'll cause water to move out of the cell. And you can see how the cell gets kind of spiky looking. They call that a hypertonic. So the way that I remember isotonic is I think equal solutes. Iso means equal. Hypotonic, think low solutes. Low solutes cause water to go into the cell. Hypertonic means high solutes, and we're always talking about the solution around the cell, okay? So it's always talking about the liquid that surrounds your sample or the cell, not what's inside of the cell itself. So water can move by this osmosis. I got all of those. Solutes can sometimes move as well, and this comes into diffusion. So while osmosis is movement of solvent, diffusion is movement of solute. It's Once again, though, it's called a passive transport because it does not require energy. It's passive transport because it happens automatically. And it's really a way of trying to spread molecules around equally. So molecules are going to move from high concentration to low concentration. So they show you this one. This is like a beaker of water and they put a couple of drops of green food coloring in. And if they just let it sit, the green food coloring will spread throughout the beaker so that it looks uniform over time. So the goal, things like to spread out, right? That's the whole chaos theory. That's all that disorder. Remember we talked about disorder. Things like to be spread out uniformly. Things don't like to be in like one concentrated corner. That's natural for things to spread out. So here's a couple of ways that that can happen. So the first one is what they call simple diffusion. So with simple diffusion, this only happens with molecules that can pass straight through the membrane. So they can pass through the cell membrane, moving from high concentration to low concentration. The only molecules that can move straight through the membrane have to be like the membrane. So the inside of the phospholipid membrane is what? Hydrophilic or hydrophobic? This part. It's hydrophobic. You're right, right? Remember, that's where those nonpolar tails are. So that whole area in the center of the membrane is hydrophobic. It does not interact with water, and it doesn't let watery molecules pass by. Polar molecules, charged molecules, ionic compounds, they can't pass through. So if this can pass through, then you know this has to be like the membrane. Okay, so only molecules that are hydrophobic have the ability to pass directly through a cell membrane. So these are molecules like gases. Oxygen and carbon dioxide, they can move from high concentration to low concentration. Oxygen moves into your cells. It moves from the blood, where it's at high concentration, and directly through the blood vessel walls, because it can pass through blood vessel walls, because it's nonpolar, passes directly through membranes, and then it can diffuse into cells. Carbon dioxide really goes the exact opposite direction. Oxygen goes in to the cell. Carbon dioxide is a gas that can actually diffuse out of the cell. And it does this because your cells make carbon dioxide. So carbon dioxide is always increasing inside of a cell. So it diffuses out of the cell, and that's how it ends up being transported back to the lungs through the blood. But they call it simple diffusion because nothing has to happen for this to work. These gas molecules can just diffuse freely. Facilitated transport, though, notice facilitated transport, the molecule has to use a channel. Right? So there's a channel that's involved. It can't just pass straight through like simple diffusion can. This is a good example of a hydrophilic molecule. Hydrophilic molecules can't get through the plasma membrane. They have to use a channel. So remember we were talking about these when we talked about the shape and structure of the cell membrane, and I told you glucose does this. So when your blood sugar is high in the blood, blood sugar it can diffuse out of the blood and into your tissues. Then when it comes to a cell that has insulin on its surface, those channels open up. They allow glucose to enter, they close and move that glucose through the channel to the other side. But notice that it's going from where there's like six little glucose balls up at the top, 6 blood sugar molecules, moves down into the cell where there's only 1. So it's going from high concentration to low concentration. So the only reason that this happens going through is because it's going from high concentration to low. Look at the next one. The next one is not passive transport. This one they call active transport. How is this one different? Yeah, it's going the exact opposite. So this active transport it's not just that it's moving molecules up, but it's moving molecules from what concentration to what concentration? Low to high. Do you see that? There's only one molecule, one little blue molecule inside of the cell, but it's getting moved out where there's already 6. So that's not passive. It's called active transport. It is going to move molecules from low concentration to high concentration. So CONC is concentration. Your cells do this in order to do work. Nerves have to do this in order to set up for a nerve impulse. Your muscles have to do this in order to be able to contract. So your cells control certain molecules to be able to put them all in here or put them all in here so that it can allow that function of the cell to happen. So nerve cells, muscle cells, they use active transport as a way to store molecules in certain parts of the cell. You can't have nerve impulses without active transport. You can't contract muscles without active transport. But what does that require? This is kind of like cleaning your house, right? If you take where there's stuff's all spread out, and I'm going to take and put it all in one place. I'm going to put all the silverware back in the silverware drawer, right? That requires work. That requires ATP. Yep, so energy is required in order for active transport to occur. Passive transport, simple diffusion, facilitated diffusion, no energy is required. That's why they call it passive transport. There is no ATP needed. It happens automatically. We have one more kind of transport that we need to talk about, and that is filtration. Certain parts of your body do filtration. Your liver filters things, your spleen filters things, but we're going to talk about the kidneys and kind of like make the analogy of how does osmosis and diffusion happen in the kidneys as a way of filtering out waste molecules and balancing water and salt concentrations in the body. Okay, so that's like the last topic of chapter 8. So we'll talk about it on Monday night. Monday night, I'll give you your exam too. You'll have a week to complete it. Okay, if you want to work on this weekend, if you look at this and you're like, oh, I want to see if I can do these, the answers for this, there's like the answer key is posted in Moodle. So you can practice those, and then that way you can actually check to see. So we'll probably go through some of them, but we'll do it on Monday.